I guess on this part over here, this is where they actually just explain a little bit more about whatever that I have explained earlier. So this slide actually explains everything, but since I have explained earlier, so I do not think I would like to repeat over on this part. So I leave it to you to have a read at it and see how that when it's shifted to the right, it's actually denoted with a minus here, just like what we mentioned just now, and the representation of it will be in reference below, in reference to the x-axis. All right, so I hope that you're clear by now on how this goes. All right, so let's move on, all right, to AC values. Okay, so usually when we want to find an average value of a waveform, okay, so what happens is that they get the area under the waveform and then they divide it by the length of the base. Okay, area above axis positive, area below axis negative. This is just like some definition and things like that. All right, basically what we need to know is that average values are also known as DC values. Okay, because it actually indicates the average value, and this is the formula basically just to indicate what this is being explained on. All right, so if we are looking at just like a sine wave, like what we have seen earlier, could be voltage, could be current, anything at all, but for the fact that we're learning AC, so we are dealing a lot with either voltage or current waveform, right? So this goes by what the formula would go. All right, so if you look at it, right, for half wave, all right, you see that it actually goes from 0 to pi, because if it's full wave, then it goes from 0 to 2 pi. All right, so if you can see that with this we have an integration, right? That's a reason how from here we actually get over here. When we integrate sine, what we get is negative cos, correct? So if you're taking negative cos, you're taking negative cos pi minus negative cos 0. all right, negative cos pi will actually give it 0, and then your cos 0 will actually give you 1. all right, that will eventually leave you with this thing over here. all right, but this just basically just sort of like for you to know about it. all right, so as you can see, E, the denotion of or notation of the slides, sometimes E also represents the V, all right, the voltage. all right, like current denoted by I. Okay, so for full wave, this is another one. If you can see that the difference is just that they actually multiply by 2. all right, but this is just more on for us to know and all that, because usually like in our tests, our exercises and stuff like that, you have to compute your own voltage and current based on what you have. Okay, also I think some of us might have heard about this before, the effective value or the RMS value. RMS basically stands for root mean square. all right, so it's actually equivalent DC value. Okay, what it basically means is that usually how many volts or amps, so because volts to indicate the voltage, amps to indicate the current. all right, for a time varying waveform. all right, usually how we get the RMS. all right, there's a way of deriving it and things like that, but by the end of it, if we are to get the effective value or the RMS value of your V, all right, you just take your peak value, you divide it with square root of 2. all right, it's also equivalent to 0.707 of your EM or VM. all right, same goes for your current. all right, you just take your peak value. If at any given point of time the question gives you a peak value and they want you to get the RMS value, just remember to just divide it by square root of 2. So that's just the rule of thumb for you to remember. all right, whatever that's been explained earlier on and all is just basically for you to understand more about it. Complex numbers. Okay, like we would have seen, this is a denotion. Let's say like a C equals to A plus JB. So J is actually the imaginary part. all right, I think we are pretty much clear with this. I'll just go very quickly with this. For example, this C equals to 6 plus J8. which means for real axis is actually 6, imaginary axis is actually 8. This is what we know as the rectangular form. Alright, if it's being represented with something and then with the angle form, we know it as polar form. Alright, so this is just the example of it. For rectangular form, 6 plus j8. 6 on the real axis and 8 on the j-axis. So this dot over here is indicating your C. Alright, if you change it in terms of your phasor diagram that we talked about earlier, alright, even with your calculator you will manage to get the equivalent phasor diagram. But the truth is, if you want to know how you actually get this tan and how you get this degree over here, it's actually what? You see, this length actually can be indicated by this line over here. Alright, you can get this, which is tan over here, by taking the square root of 6 square plus 8 square. Alright, that's how you get the tan over here. And your degree is actually by you getting the inverse tangent of your y over x, because you want to get the angle in between this part here. If you go by the trigo law as well, you know that tangent theta is equivalent to y over x, right? So you take inverse tangent 8 divided by your 6, that's where you get 53.13. Alright, that's the equivalent polar form. Phasor diagram, polar form. If it's in terms of this kind of diagram here, we call it the rectangular form. Alright, so just as what I've explained earlier on. Okay, this is some Pythagoras theorem. You have learned this last time, so I don't go too far away from it. Power of j. Alright, j basically it actually basically means it's a square root of -1. At any point of time, if you have j square, it's also equivalent to -1. Yeah, so that's just the important thing that you would need to know. In terms of how you actually plot it, I think you are pretty clear about it, right? For multiplication or division, how do we multiply two polar forms together? Alright, if it's the magnitude, the number itself, alright, so you just take it by a multiplied by b. Alright, but for the degree itself, alright, for multiplication, what you do is you plus 2 degrees together. If it's a division, alright, the a will divide by b, and then your face, you will take it and subtract it with the other one. Alright, so this is just I think you would have learned this in maths, so I'm not going to go through very thoroughly about it. 1 over c with the phasor form at the reciprocal area here, it can also be indicated of its equivalent over here. Okay, conjugate just basically means if your face is positive, then you change it to negative, and the other way around. Okay, same real part but opposite imaginary part. So for example, conjugate of 6 plus j8 will be equivalent to 6 minus j8. If it's minus, then it's plus. So just that. Alright, so this is some examples of how it is. You may give it a try on your calculator. Now I would like to move on to purely resistive circuit. And so from earlier on until now, we have learned all about the terminology, how to sketch the wave diagram, and then how to draw the phasor diagram, how to differentiate whether something is lagging or leading, and how to differentiate whether the phase is of minus or plus. Alright, so we're going to learn more a little bit and move on to circuits. Okay.